These are the numbers that make our entire galaxy look like a speck of dust floating inside something almost too large to describe. This is what happens when you actually try to measure the Milky Way, the black hole sitting at its center, and the vast structure of galaxies surrounding it, and stack those numbers up against the size of everything else in the universe. If you've ever looked up at the night sky and felt small, you had no idea how small you actually are. Stick around, because by the end of this video, the sky is never going to look the same again. If that sounds like your kind of rabbit hole, hit like on this video and subscribe to the channel, because we go down these rabbit holes often, and you don't want to miss the next one. Let's start with the galaxy you're sitting in right now. For most of human history, nobody knew what the Milky Way actually was. People saw a pale band of light stretched across the night sky and had no framework for understanding it. That changed slowly, piece by piece, starting more than 2,000 years ago with the ancient Greek philosopher Democritus, who proposed that this band of light was actually made up of individual stars, too faint and too close together for the human eye to separate. He was right. It would take roughly 2,000 more years for anyone to prove it, and even longer to figure out just how big the thing actually was. Today, astronomers describe the Milky Way as a barred spiral galaxy. That means it has a central bar-shaped structure of stars running through its middle, with spiral arms curling outward from that bar like the arms of a pinwheel. If you could rise up above the plane of the galaxy and look down on it from directly overhead, that's roughly the shape you'd see: a flattened disk, thicker in the middle, thinner at the edges, with long spiral arms trailing around a dense central bulge. Now here's where things get interesting, because even professional astronomers don't agree on exactly how big this thing is. The number you'll hear most often, the one repeated in textbooks and documentaries and NASA fact sheets, is that the Milky Way is about 100,000 light-years across. NASA's own Imagine the Universe project states the galaxy is approximately 100,000 light-years in diameter. The Las Cumbres Observatory gives the same figure. Space.com lists the same figure. It's become something like the official number, in the sense that it's the one that gets repeated the most. But if you actually go looking through the astronomical literature, the picture is messier than that. A more precise measurement technique, based on something called the D25 isophote, a specific brightness threshold used to define where a galaxy's visible disk effectively ends, gives a smaller figure, about 26.8 kiloparsecs, which works out to roughly 87,400 light-years, give or take about 3,600 light-years of uncertainty. Other sources describe the full galactic disk, including its more diffuse outer regions, as stretching somewhere between 170,000 and 200,000 light-years across. So depending on exactly where you decide the galaxy ends, and different astronomers draw that line in different places, the Milky Way could reasonably be described as anywhere from about 87,000 light-years across to as much as 200,000 light-years across. That's not a small range. That's a difference of well over 100,000 light-years, roughly the width of the more conservative estimate of the entire galaxy, just sitting there as a margin of uncertainty. This is so hard to pin down because a galaxy doesn't have a hard edge, the way a planet or a coin does, and there's no wall where the Milky Way just stops. Instead, the number of stars simply gets thinner and thinner and thinner as you move outward from the center, fading gradually into the near emptiness of intergalactic space, rather than cutting off cleanly. Astronomers have found that beyond a radius of about 40,000 light-years from the center, the star count starts dropping off noticeably faster, for reasons that are still not fully understood. Trying to measure the size of something that fades out gradually, instead of ending abruptly, is a bit like trying to measure exactly where a cloud stops. You can do it, but the answer depends heavily on where you decide thin enough to not count anymore begins. The disk itself is remarkably flat, at least by galactic standards. While the Milky Way is around 100,000 light-years across, using the most commonly cited figure, it's only about 1,000 light-years thick on average. If you scale that down and picture the galaxy as roughly the size of a large dinner plate, the thickness of that plate, relative to its width, would be thinner than a sheet of paper. Some more recent measurements of the gaseous component of the disk, as opposed to just the stars, suggest it may actually be about twice as thick as previously believed, closer to 12,000 light-years for the gas layer specifically, although the star-filled portion remains close to that 1,000 light-year figure. At the very center of all of this sits a bulge, a dense, roughly spherical clump of stars packed in around the galactic core, about 10,000 light-years across on its own. If our solar system happened to be located inside that bulge instead of out in the suburbs of the galaxy, the night sky would look completely alien. Astronomers estimate that from inside the bulge, you'd be able to see roughly 1 million stars as bright as Sirius, the brightest star currently visible in Earth's night sky. The night wouldn't really get dark at all. It would stay lit, dimly but constantly, by the sheer density of starlight surrounding you. We are not in the bulge. We'll get to exactly where we are in a moment. But first, let's deal with the other number nobody can quite agree on. How many stars are actually in this galaxy? If you ask how many stars make up the Milky Way, you will get a different answer depending on who you ask, and depending on when you ask them. Some sources put the number at a minimum of 100 billion stars, with an upper bound of 400 billion. Others land on a rounder middle figure of about 200 billion. Still others, including a well-publicized 360-degree imaging project out of the University of Wisconsin, describe the galaxy as home to more than 300 billion stars. Every one of these numbers gets cited by credible sources, and none of them is simply wrong. They're all estimates, and the estimates disagree with each other by a factor of 4. The reason for that disagreement comes down to something surprisingly mundane. Dim stars are hard to see. The vast majority of stars in any galaxy, including ours, aren't bright sun-like stars. They're small, cool, low-mass dwarf stars, some of them barely more massive than large planets, and they put out so little light that astronomers can only detect them nearby, typically within a few hundred light-years of Earth. Beyond that range, they simply fade below the threshold of what our telescopes can pick out against the darkness. So when astronomers try to count all the stars in the Milky Way, they're not actually counting them one by one. They're modeling the galaxy's total mass and brightness, and then estimating downward into stars we can't directly see. Different models, built on different assumptions about how many faint dwarf stars are hiding out there, produce different totals. That's the entire reason the number swings between 100 billion and 400 billion. For comparison, our nearest large galactic neighbor, Andromeda, is estimated to contain around 1 trillion stars, roughly 2.5 to 10 times as many as our own galaxy, depending on which Milky Way estimate you're using. We'll come back to Andromeda later, because it plays a much bigger role in this story than you might expect. As for how old the Milky Way actually is, current estimates put the galaxy's age at around 13.6 billion years, with NASA's own materials describing it as having formed approximately 14 billion years ago. Given that the universe itself is only about 13.8 billion years old, that means our galaxy has existed for almost the entire history of the universe. It started forming not long after the Big Bang itself. The oldest known individual star within the Milky Way is estimated at about 13.2 billion years old, meaning there are stars still burning in our own galaxy today that ignited when the universe itself was practically brand new. So here's where we stand so far. We live inside a galaxy that is, depending on how you measure it, somewhere between 87,000 and 200,000 light-years across, containing somewhere between 100 billion and 400 billion stars, that has existed for nearly the entire 13.8 billion year history of the universe. And we haven't even gotten to where we actually sit inside that structure yet. Let's fix our location. Our solar system is not near the center of the Milky Way, and it is not near the edge either. We sit somewhere in the middle distance, out in what you could reasonably call the suburbs of the galaxy. Different sources give slightly different figures for exactly how far we are from the galactic center. NASA's Imagine the Universe page states the solar system sits about 26,000 light-years from the center. Britannica gives a slightly larger figure, around 30,000 light-years. Other astronomical data place us somewhere between 24,000 and 28,000 light-years out. As with the size of the galaxy itself, there's a real range here, rather than one single agreed-upon number. But all of these estimates land in the same general neighborhood, tens of thousands of light-years from the core, roughly 1/3 to 2/3 of the way out toward the edge, depending on which overall diameter figure you're using as your reference point. We're not just sitting in some random featureless patch of the disk either. we're located within a specific structural feature of the galaxy called the Orion Arm, sometimes called the Orion Spur, a relatively minor, shorter arm segment sandwiched between two of the galaxy's larger, more prominent spiral arms, the Sagittarius Arm and the Perseus Arm. If the Milky Way's major spiral arms are like the main highways of the galaxy, the Orion Arm is more like a side road connecting two of them. It's not nothing. It contains plenty of stars, including our own Sun, but it's not one of the galaxy's grand architectural features either. There's another detail about our position that's easy to overlook. We're not sitting perfectly still within the galactic disk, and we're not perfectly centered on the disk's midplane. According to more detailed studies of the Sun's motion, we currently sit somewhere around 50 to 60 light-years above the galactic midplane, and we're slowly oscillating, bobbing up and down through the disk over time, in a cycle that takes roughly 60 to 70 million years to complete one full bob. A separate estimate from the Las Cumbres Observatory puts the Sun even closer to the plane, at just 95 light-years from center. Either way, we're close to the middle of that 1,000 light-year thick disk, but we're not frozen in place. We're drifting slowly up, then slowly back down, then up again, over tens of millions of years, while at the same time doing something far bigger and far faster, orbiting the entire galactic center. That orbit is where the truly strange numbers start to show up. Right now, as you're watching this, you are not standing still. You never have been. Earth spins on its axis. Earth orbits the Sun, and the entire solar system, Sun included, is hurtling around the center of the Milky Way at a speed that's difficult to process in ordinary terms. Multiple sources converge on a figure of roughly 220 to 230 kilometers per second, with some measurements running as high as 251 kilometers per second. Converted into more familiar units, that works out to approximately 828,000 kilometers per hour, or about 514,000 miles per hour. NASA's own Starchild Education project rounds this to an average velocity of 828,000 kilometers per hour. To put that speed into perspective, at that velocity, you could circle the entire equator of the Earth in about 2 minutes and 54 seconds. EarthSky has calculated that in just 90 seconds, our solar system covers roughly 12,500 miles, about 20,000 kilometers, purely from this orbital motion around the galactic center. We are moving through space, right now, at roughly 1/1300th the speed of light. And here's the part that actually breaks people's sense of scale. Even moving that fast, it still takes the Sun somewhere between 225 and 250 million years to complete a single orbit around the center of the galaxy. Different research groups have landed on slightly different precise figures. 226 million years according to the National Radio Astronomy Observatory, 220 to 230 million years according to University of Texas at Austin astronomer Keith Hawkins, 225 million years in some references, but they all cluster in that same broad window. This single orbit has a name. Astronomers call it a galactic year, or sometimes a cosmic year. Think about what fits inside just one of those years. 225 million years ago, dinosaurs had not yet risen to dominance on Earth. The first true dinosaurs were only just beginning to appear in the fossil record. Entire geological eras, the rise and fall of the dinosaurs, the asteroid impact that ended their reign, the subsequent 66 million year rise of mammals, the entire evolutionary path that eventually produced human beings. All of that happened within a single lap of our solar system around the Milky Way's center. We haven't even finished one galactic year since dinosaurs first started showing up. Since the solar system itself formed, roughly 4.6 billion years ago, it has completed only about 20 of these galactic years. 20 full orbits around the center of our own galaxy. 20 laps. That's the entire lifespan of the Sun and its planets, measured on the galaxy's own clock. So here's the picture so far. We're on a rock, orbiting a star, that is itself flying around the center of a 100,000 light-year wide structure at 500,000 miles an hour. And even at that speed, one single orbit takes 250 million years. And at the center of everything we're orbiting around sits something you cannot see with your eyes, but that astronomers have now managed to photograph directly. At the exact center of the Milky Way, sits an object called Sagittarius A. Pronounced Sagittarius A star. It is a supermassive black hole, and everything in the galaxy, including our Sun, including Earth, including you, is slowly circling around it. The object itself was first detected decades before anyone understood what it truly was, and its story actually begins even earlier, with an accidental discovery eerily similar to the one that would later reveal the cosmic microwave background. In the early 1930s, physicist Karl Jansky, working for Bell Telephone Laboratories, was trying to track down the source of static interference that might disrupt transatlantic phone calls when he identified a persistent radio hiss coming from the direction of the constellation Sagittarius. That signal turned out to be coming from the center of our own galaxy, marking the effective birth of radio astronomy as a field. Decades later, in 1951, Australian radio astronomers narrowed that emission down further, confirming it was coming specifically from the galaxy's core. Then, on February 13 and 15, 1974, astronomers Bruce Ballack and Robert Brown, using a radio interferometer at the National Radio Astronomy Observatory's Green Bank facility in West Virginia, finally isolated a small, unusually bright, compact radio source sitting at the very center of that emission, nested within a larger, already known region of radio noise called Sagittarius A. The name Sagittarius A itself didn't actually appear until 1982, when Brown proposed it, borrowing the asterisk notation from atomic physics, where it's used to denote atoms in an excited, high-energy state, a fitting label for a compact object apparently pumping enormous amounts of energy into its surroundings. For years afterward, the object's true nature remained genuinely uncertain, one plausible explanation among several, until later infrared and orbital studies, including the work that eventually earned Genzel and Ghez their Nobel Prize, built up the overwhelming case that it had to be a supermassive black hole. The numbers here are almost as strange as the object itself. Sagittarius A has a mass of approximately 4 million times the mass of our Sun, with the most precise measurement putting the figure at 4.1 million solar masses. And yet, according to the imaging released by the Event Horizon Telescope collaboration, all of that mass, 4 million suns worth of matter, is packed into a region smaller than the orbit of the planet Mercury around our own Sun. We didn't always know this for certain. For decades, astronomers suspected something massive and invisible was sitting at the galactic center, based on the way nearby stars behaved. But proving it required watching individual stars orbit that invisible point for years, sometimes decades, and tracking exactly how fast they moved. Two research teams did exactly that, one led by Reinhard Genzel at the Max Planck Institute, the other by Andrea Ghez at UCLA. Both groups tracked stars orbiting impossibly close to the galactic center, some completing full orbits in as little as roughly 15 years, which, for context, is faster than several planets in our own solar system orbit the Sun. By measuring how those stars moved, both teams independently calculated the same conclusion. There had to be an object with the mass of about 4 million suns concentrated in an extraordinarily small space, and the only object physics allows to exist under those conditions is a supermassive black hole. Genzel has stated that his team pinned down the black hole's mass to an accuracy of 0.1%, and its distance from Earth to an accuracy of about 0.2%. That work earned Genzel and Ghez a shared half of the 2020 Nobel Prize in Physics, with the other half going to Roger Penrose for his related theoretical work proving that black hole formation is a robust prediction of general relativity. For most of astronomical history, all of that evidence was indirect. Nobody had ever actually seen the thing itself, only its gravitational fingerprints on the stars around it. That changed on May 12, 2022, when the Event Horizon Telescope collaboration released the first ever direct image of Sagittarius A, showing a glowing ring of superheated gas surrounding a dark central shadow, the visual signature of a black hole's event horizon. It was only the second black hole ever directly imaged by humanity, following the same collaboration's 2019 image of an even larger black hole, M87, at the center of the distant galaxy Messier 87. Photographing Sagittarius A was an extraordinary technical achievement, mostly because of how far away it is and how small it appears from here. The black hole sits roughly 25,000 to 27,000 light-years from Earth, and researchers at Caltech described the difficulty of imaging it this way. It was, in their words, comparable to taking a photograph of a single grain of salt in New York City, using a camera located in Los Angeles. To pull that off, the Event Horizon Telescope team linked together 8 radio telescopes spread across multiple sites around the entire planet, effectively turning Earth itself into one giant telescope using a technique called very long baseline interferometry. So there it is, sitting at the exact center of everything we've been describing, an invisible object with the mass of 4 million suns, crammed into a space smaller than Mercury's orbit, 25,000 plus light-years away from the rock you're sitting on right now, quietly anchoring the gravitational dance of every star, including ours, in the entire galaxy. For most of human history, we didn't know any of this. We didn't even know the Milky Way was the whole universe, let alone that it had a monster like this sitting at its heart. Figuring that much out took a surprisingly short, surprisingly dramatic chapter of scientific history, and it happened almost entirely within the lifetime of people whose grandchildren are alive today. Until the early 1920s, many of the world's leading astronomers believed the Milky Way was the entire universe, not part of it, all of it. Everything that existed, as far as anyone could prove, was contained within our own galaxy. That belief wasn't unreasonable at the time. It was simply the best conclusion the available evidence supported. Starting in 1915 and continuing through 1918, astronomer Harlow Shapley used Cepheid variable stars, a special class of star whose brightness pulses in a predictable, measurable pattern, to map out the globular clusters surrounding the Milky Way. Based on that work, Shapley concluded the galaxy was enormous, roughly 300,000 light-years across by his estimate, far bigger than anyone had previously proposed, and that the Sun sat roughly 50,000 light-years from its center. A few years earlier, in 1917, Shapley had also produced the first reliable size measurement of the Milky Way at all, landing on a figure of about 100,000 light-years, a number that, as Britannica notes, has held up remarkably well in the century since. But there was a competing idea circulating in astronomy at the time, centered on strange, faint, cloudy smudges of light visible through telescopes, known as spiral nebulae. Some astronomers, including Heber Curtis at the Lick Observatory, believed these spiral nebulae weren't clouds of gas inside our own galaxy at all. Curtis argued they were entire separate galaxies in their own right, comparable in size to the Milky Way, but sitting at such enormous distances that they appeared as nothing more than faint smudges from Earth. This idea became known as the island universe theory. On April 26, 1920, these two competing views collided head-on at the Smithsonian Institution in Washington, D.C., in what became known as astronomy's Great Debate. Shapley argued the Milky Way was the entire universe, and the spiral nebulae were small, nearby objects contained within it. Curtis argued the opposite, that these nebulae were independent, distant galaxies. Multiple historical accounts describe the debate's outcome as inconclusive, something close to a draw, and in a strange twist, both men turned out to be partly right and partly wrong. Curtis correctly identified the spiral nebulae as separate galaxies, but Shapley had a more accurate handle on the true size of our own galaxy. It would take just 3 more years to settle the question for good, and it came down to one astronomer, one telescope, and one flickering star. On the night of October 5th into October 6th, 1923, Edwin Hubble was reviewing photographic plates taken with the 100-inch Hooker telescope at Mount Wilson Observatory, searching for novae, exploding stars, within the Andromeda Nebula. Instead, he noticed something else, a star that brightened and dimmed in a pattern he recognized as a Cepheid variable, the exact type of star Shapley had used years earlier to measure the Milky Way itself. Hubble reportedly marked the plate with the notation VAR in red ink, unable to contain his excitement at what he'd found. Over the following weeks and months, Hubble tracked that star's pulsing pattern and used it to calculate its distance. By the end of 1924, he had found and measured a total of 12 Cepheid variables within Andromeda, and the numbers all pointed to the same staggering conclusion. Andromeda sat approximately 900,000 light-years away. Later sources round the figure to about 930,000. Even that number turned out to be a significant underestimate, since Hubble hadn't yet accounted for the existence of two distinct types of Cepheid variable stars. The true distance to Andromeda is closer to 2.5 million light-years. But even the underestimated figure was already more than enough. It was already 3 times larger than the entire size of the universe Shapley had proposed just a few years earlier. There was no way Andromeda could be a nearby cloud of gas inside the Milky Way. It had to be a separate galaxy entirely, sitting almost 1 million light-years away at minimum. Hubble wrote to Shapley to share the discovery. According to an account published by The Conversation, Shapley's reaction upon reading the letter was to remark, "Here is the letter that destroyed my universe." By 1925, Hubble's findings had been formally presented to the astronomical community, and the great debate was effectively over. Decades later, astronomer Alan Sandage would summarize the shift in understanding this way. No one knew what galaxies actually were before 1900. Few people knew by 1920, but all astronomers knew after 1924. In the space of about 4 years, humanity went from believing the Milky Way was everything to understanding it was just one galaxy among what we now know to be an almost incomprehensible number of others. And it's worth pointing out that none of this would have been possible without a discovery made over a decade earlier by astronomer Henrietta Leavitt, who in 1912 identified the underlying relationship between a Cepheid star's brightness and its pulsing period, using stars she observed in the Magellanic Clouds. That relationship became the standard candle technique that let Shapley measure the Milky Way, and later let Hubble measure the distance to Andromeda. The tool that shattered our understanding of the size of the universe was built by a woman most people have never heard of. Speaking of Andromeda, it's not just a footnote in the history of how we discovered galaxies. It's also, eventually, going to become part of our own galaxy's story, in a much more literal sense. Andromeda sits about 2.5 million light-years from the Milky Way, which makes it, by a wide margin, the most distant object you can see with your own naked eye, no telescope required, if you know where to look on a dark, clear night. Because it's 2.5 million light-years away, the light reaching your eyes right now left Andromeda 2.5 million years ago, back before modern humans existed at all. Andromeda is bigger than our own galaxy. It's commonly described as roughly twice the size of the Milky Way, and it's estimated to contain around 1 trillion stars, compared to our own galaxy's 100 to 400 billion. And it's not just sitting there quietly, it's moving toward us. Astronomers first suspected this over a century ago. In the early 1900s, an astronomer named Vesto Slipher measured the light coming from Andromeda and noticed it was blue-shifted, a telltale sign in astronomy that an object is moving toward the observer rather than away from it. Based on that measurement, Slipher predicted Andromeda was headed directly toward the Milky Way. It took until 2012 for Hubble Space Telescope data to fully confirm that prediction. The two galaxies really are on a collision course. For years, the story told in documentaries, including plenty of videos just like this one, went something like this. In about 4 to 4.5 billion years, Andromeda and the Milky Way will collide, and somewhere between 6 and 10 billion years from now, the two will have fully merged into a single new galaxy, nicknamed Milkomeda, or sometimes Milkdromeda. In August 2020, research using Hubble Space Telescope data on Andromeda's surrounding halo of gas, a project called Omega, found that in one sense, the collision has already begun, since Andromeda's extended gas halo already overlaps with our own galaxies. Here's where the story gets a genuine, honest twist. The kind you don't often hear in these videos, because it only became clear very recently. In 2025, new research revisited the whole scenario, and the headline finding, reported by Space.com, was blunt. The certainty of this collision has gone, in their words, from near certainty to a coin flip. The updated analysis found that once you properly account for the uncertainties in the current positions, motions, and masses of all the relevant galaxies, including the Triangulum Galaxy and other members of our local group, there's really only about a 50% chance that the Milky Way and Andromeda actually merge within the next 10 billion years at all. The same study found less than a 2% chance of a true head-on collision. In most of the merger scenarios that do happen, the two galaxies would first swing past each other, lose orbital energy in the process, and then gradually spiral together over a longer stretch of time. But if that first close pass isn't close enough, if the galaxies pass each other at a separation of more than roughly 500,000 light-years, they might not merge at all within that time frame. So the collision that's been presented as an inevitability for years is, as of the most current research, something closer to a coin flip. That's not a knock against the earlier science. It's what happens when better data and better models come along. It's also a pretty fitting detail for a video about how small and uncertain our place in the universe really is. Even the fate of our own galaxy isn't fully settled. If the merger does happen, individual stars almost certainly won't collide with each other. Stars, even in a densely packed galaxy, are separated by such enormous distances, on average around 100 billion miles apart, that one description compares it to placing a single ping-pong ball every 2 miles. Two galaxies can pass directly through each other, star by star, without a single head-on collision, simply because there's so much empty space between every individual star. Our own solar system would likely be flung outward, toward the edge of whatever new galaxy results, with only a small chance of being ejected from it completely. And because the Sun has an estimated 7.6 billion years of life left in it, it would still be around, still burning, for the earlier stages of whatever does eventually happen. Whether or not Andromeda and the Milky Way actually merge, the two galaxies are part of something much larger, a structure that puts even Andromeda's trillion stars in perspective. The Milky Way and Andromeda are the two largest members of a much bigger collection of galaxies called the Local Group. Alongside those two giants, the Local Group also includes the Triangulum Galaxy, the third largest member, plus roughly 50 or more much smaller dwarf galaxies scattered around them, all loosely bound together by gravity. The Triangulum Galaxy, also known as M33, deserves a moment of its own, because it's a genuinely strange case study in how uncertain even settled astronomical facts can be. It sits somewhere between about 2.4 and 3 million light-years away. Sources vary within that range, depending on the specific measurement technique used. Roughly half the size of the Milky Way, at about 50,000 to 60,000 light-years across, and holds an estimated 40 billion stars, less than half our own galaxy's population. Unlike both Andromeda and the Milky Way, Triangulum has no central bar. Its spiral arms extend directly from its core, more loosely wound and less structured than its two larger neighbors. It's faint enough, at an apparent magnitude of about 5.7, that it's often cited as the most distant object a human eye can spot, without a telescope under truly dark skies, though it's genuinely difficult to see, precisely because its light is spread across such a wide patch of sky, rather than concentrated in one bright point, and plenty of experienced stargazers have looked directly at it without realizing it was there. Its history follows the same broad pattern as Andromeda's. For decades, astronomers weren't sure whether it was a nearby gas cloud or a separate galaxy, until Edwin Hubble identified dozens of Cepheid variable stars within it in the 1920s and used them to prove, once again, that it sat millions of light-years beyond the edge of our own galaxy. And Triangulum may not even be fully independent of Andromeda. Multiple sources describe it as possibly gravitationally bound to, or even trapped in orbit around, the larger Andromeda galaxy, with observations showing it closing in on the Milky Way's general direction at roughly 62,000 miles per hour, caught up, one way or another, in the same slow gravitational dance as its much larger neighbor. Below those three giants, the roughly 50-plus dwarf galaxies making up the rest of the Local Group are, individually, almost nothing by comparison, some holding only a few million stars, faint enough that new ones are still being turned up in survey data on a fairly regular basis. Even a structure as close and thoroughly studied as our own Local Group, the single most nearby collection of galaxies in the entire universe, hasn't been completely mapped out. Astronomers are still finding new members of our own galactic neighborhood, tucked into the gaps between the objects we already know about. Zoom out further, and the Local Group itself turns out to be just one small piece of an even bigger structure, the Virgo supercluster, sometimes called the local supercluster, estimated at roughly 110 million light-years across. And then, in 2014, astronomers led by Brent Tully published research in the journal Nature Redefining Our Cosmic Neighborhood, on an even grander scale. Using newly available data on the precise motions and distances of thousands of galaxies, roughly 8,000 of them, they identified a structure so large it needed an entirely new name. They called it Laniakea, a Hawaiian word meaning immeasurable heaven, suggested by Nawaa Napoleon, a professor of Hawaiian language at Kapiolani Community College. The numbers involved in Laniakea are almost absurd. It spans roughly 500 million light-years across. Some sources give a slightly more precise figure of 520 million light-years, and contains an estimated 100,000 galaxies, with some estimates running as high as 150,000. Its total mass has been calculated at around 10 to the 17th power times the mass of our Sun. That's a 1, followed by 17 zeros, which one source describes as roughly 100,000 times the mass of the entire Milky Way, all by itself. And our galaxy isn't even anywhere near the center of this structure. The Milky Way sits out near Laniakea's edge, close to the fringe of the whole supercluster, not at some privileged central location. Within Laniakea, galaxies flow inward along enormous filaments of matter, drawn toward a gravitational focal point researchers call the Great Attractor. In much the same way, water flows downhill into a valley. It's a genuinely useful way to picture it. An entire supercluster of galaxies, ours among them, all gently sliding toward one shared gravitational low point. That gravitational low point deserves a little more attention because it's one of the stranger open mysteries in modern astronomy. Astronomers first noticed something odd back in the early 1970s. Hundreds of nearby elliptical galaxies, along with our own local group, appeared to be drifting through space in a coordinated direction, being pulled by something with an estimated mass on the order of 10 to the 16th power times the mass of our Sun. The problem is that the calculated direction of that pull points almost directly behind the flat disk of our own galaxy, into a region astronomers call the zone of avoidance, where dust, gas, and the sheer density of foreground Milky Way stars block roughly 20% of the entire extragalactic sky from being observed in ordinary visible light. In other words, the single largest concentration of mass in our immediate cosmic neighborhood, the thing that's been quietly steering the motion of our own galaxy and thousands of others for billions of years, happens to sit directly behind our own galactic disk, hidden from ordinary telescopes by the very structure we live inside. Astronomers have had to work around that blind spot using longer wavelengths of light, infrared and radio and X-ray observations that can punch through the dust and stars that block visible light, in painstaking, decades-long survey work to map what actually lies in that hidden zone. That work has identified a massive galaxy cluster called the Norma cluster as likely sitting at or near the heart of the Great Attractor's gravitational pull, though because of the zone of avoidance, dedicated surveys are still actively discovering new galaxies in that region today, and the full picture remains genuinely incomplete. It's a strange thing to sit with. The largest nearby structure steering the motion of our entire local group is one we still can't fully see directly, simply because our own galaxy happens to be standing in the way, and the Great Attractor turned out not to be the whole story. In 2017, a team led by Yehuda Hoffman at the Hebrew University of Jerusalem, working with astronomer Brent Tully, the same researcher who had identified Laniakea 3 years earlier, published a study in the journal Nature Astronomy, revealing that the Milky Way isn't just being pulled toward the Great Attractor and the more distant Shapley concentration beyond it. We're also being pushed from almost the exact opposite direction by an enormous, largely empty region of space the team named the dipole repeller. Rather than exerting an actual repulsive force, the void appears to work by absence. It's an area with far fewer galaxies than the surrounding cosmic average, and the gravity of everything around it, most of it concentrated toward the Great Attractor and Shapley concentration on the far side, effectively drains our region of space away from the emptiness and toward the crowd. As Hoffman put it at the time, it has become apparent that push and pull are of comparable importance at our location. The net result is a galaxy caught in a gravitational tug-of-war on a scale of more than 1 billion light-years, pulled from one side by a supercluster we can barely see because our own galactic disk is in the way, and pushed from the other by a void so empty that its own emptiness became detectable only through the motion it left behind in everything around it. But here's a twist that even a lot of documentaries about Laniakea leave out. Follow-up research after the original 2014 discovery found that the galaxies within Laniakea are not actually gravitationally bound to one another, the way, say, the Sun and Earth are bound together. That means Laniakea isn't a permanent structure. Because the universe's expansion keeps stretching space itself, pulling everything apart at ever-increasing rates over cosmic time, Laniakea is expected to slowly dissolve rather than stay together indefinitely. Right now, we happen to live inside a supercluster large enough to contain 100,000 galaxies, and even that isn't going to last forever. For a sense of just one piece of what's inside Laniakea, the Virgo cluster alone, a smaller structure within the larger supercluster, contains more than 1,000 galaxies, roughly comparable in size to our own, located about 50 to 60 million light-years from Earth. That's just one neighborhood within Laniakea. There are dozens of comparable clusters and groups making up the rest of it. So far, we've gone from a solar system, to a galaxy, to a local group, to a supercluster spanning 500 million light-years and containing on the order of 100,000 galaxies. And we're still not at the top. The universe itself is approximately 13.787 billion years old, a figure almost always rounded to 13.8 billion years. Given how long light takes to travel, you might expect that we could only ever see out to a distance of 13.8 billion light-years in any direction, since light hasn't had any more time than that to reach us. But the actual figure astronomers give for the diameter of the observable universe, the portion of the universe whose light has had time to reach Earth since the Big Bang, is roughly 92 to 93 billion light-years across, with a radius of about 46 to 46.5 billion light-years. That gap between 13.8 billion years of travel time and 92 billion light-years of actual distance confuses a lot of people, understandably, and it's worth explaining, because it's not a mistake, it's a direct consequence of how the universe actually works. Space itself has been continuously expanding for the entire 13.8 billion year history of the universe. The earliest light we can detect left its source a very long time ago, and during that light's entire journey toward us, the space it was traveling through kept stretching. So the regions that emitted that ancient light aren't 13.8 billion light-years away anymore. They've been carried much farther away by the ongoing expansion of space itself, even while their light was still in transit toward Earth. This has been addressed directly in peer-reviewed cosmology, notably in a paper titled Expanding Confusion by researchers Tamara Davis and Charles Lineweaver. And it doesn't violate anything in relativity, because no signal is ever locally traveling faster than light. It's the space in between that's stretching, not the light itself breaking any speed limit. The number of galaxies that actually exist inside that 93 billion light-year sphere turns out to be another figure with a genuinely interesting evolving history, worth walking through as a case study in how science updates its own conclusions. For a long stretch of time, the widely cited estimate was somewhere around 100 to 120 billion galaxies in the observable universe. Then, in a study published around 2016, led by astronomer Christopher Consolis, researchers used three-dimensional reconstructions built from deep Hubble Space Telescope images, combined with new mathematical modeling, and came to a dramatically different conclusion. The true number was closer to 2 trillion galaxies, roughly 10 times higher than the old estimate. Their reasoning was that in order for the visible galaxy counts and masses to add up correctly, there had to be a huge population of extremely faint, extremely distant galaxies that current telescopes simply can't detect yet, on the order of 90% of all galaxies in the observable universe, hiding just beyond the edge of our current instrument's sensitivity. That 2 trillion figure became the new headline number, repeated across science media for years. But more recent analysis, referencing data gathered from NASA's New Horizons spacecraft around 2021, revised that estimate back downward again, to a range of only a few hundred billion galaxies, sharply lower than the 2 trillion figure that had just become the accepted wisdom. Both figures, the 2 trillion and the several hundred billion, show up in credible, recent sourcing, which tells you this isn't settled. It's a live, ongoing scientific debate, And the honest answer to how many galaxies are in the universe is that nobody actually knows for certain. The estimate has swung by a factor of 10 or more within the last decade alone, and it may well swing again. And that's just the observable universe, the part we can actually detect. The true total size of the entire universe, beyond what light has had time to reach us from, is unknown. Some research even suggests the universe could be infinite in extent, which, if true, would mean there's no upper limit at all on the true number of galaxies out there, only a limit on how many we happen to be able to see from our one particular vantage point in space and time. To give you one sense of just how large individual galaxies can get, the current record holder for largest known galaxy is thought to be ESO 383-76, a supergiant elliptical galaxy located in the constellation Centaurus, roughly 654 million light-years from Earth. Depending on which measurement you use, it spans somewhere between about 717,000 and 1,764,000 light-years in diameter. Even using the smaller of those two figures, that galaxy is more than 7 times the width of our own Milky Way. Using the larger figure, it's more than 17 times as wide. Somewhere out there, galaxies exist that make our own 100,000 light-year wide home look like a rounding error. We've now gone all the way up, from our solar system to a galaxy, to a supercluster, to the entire observable universe. Let's flip the perspective completely and go back down, because the smallness doesn't stop at the edge of the Milky Way. It starts a lot closer to home than that. Before we can appreciate how small the Milky Way is next to everything else, it's worth appreciating how small our own solar system is compared to the Milky Way, because most people badly underestimate this too. Start with the basic unit astronomers use for distances inside a solar system, the astronomical unit, or AU, which is simply the average distance between the Earth and the Sun, about 150 million kilometers, or roughly 93 million miles. Neptune, the outermost official planet, orbits at about 30 AU from the Sun. That already sounds like a big number, 30 times the Earth-Sun distance, but it's nothing compared to what comes next. Beyond Neptune, our solar system doesn't just stop. It extends out into a vast, sparse region called the Oort cloud, a shell of icy bodies still gravitationally bound to the Sun, believed to be the source of long-period comets. The Oort cloud's outer edge extends out to roughly 100,000 AUs from the Sun, which works out to somewhere between about 1.87 and 2.1 light-years. That means our solar system, including its outermost gravitational reach, is roughly 2 light-years across, at minimum, on its own. We actually have a real physical object that's been testing the true scale of this out for nearly 50 years. Voyager 1, launched by NASA on September 5, 1977, and still, to this day, the most distant human-made object in existence. Voyager 1 crossed the heliopause, the boundary marking the edge of the Sun's solar wind influence, and officially entered interstellar space on August 25, 2012. It's currently traveling at roughly 38,000 miles per hour, about 17 kilometers per second, and on November 15, 2026, it's projected to become the first human-made object to reach a distance of 1 full light day from Earth, about 16 billion miles, or 26 billion kilometers away. And here's the number that should really put things in perspective. Voyager 1 has been traveling continuously at nearly 40,000 miles per hour for almost 50 years, and despite that, it still hasn't even reached the inner edge of the Oort cloud yet. NASA estimates it will take Voyager 1 roughly another 300 years just to reach that inner edge, and then another 30,000 years beyond that to fully cross through and exit the far side of the cloud. Half a century of non-stop travel at 38,000 miles an hour, and the fastest, farthest traveling object humanity has ever built still hasn't left our own solar system's outer shell, let alone reached another star. Speaking of other stars, the nearest star system to our own Sun, Alpha Centauri, including the small red dwarf Proxima Centauri, sits about 4.2 light-years away, roughly 270,000 AU. At Voyager 1's current speed, covering that distance would take approximately 70,000 years, though, for what it's worth, Voyager 1 isn't actually headed in that direction at all. Put all of that together, and you get a genuinely useful mental picture. Our solar system, Sun, planets, and the outer edge of the Oort cloud included, is roughly 2 light-years across. The Milky Way, at even the smallest commonly cited figure, is around 87,000 light-years across. That means our entire solar system, the Sun, all 8 planets, every moon, every asteroid, every comet we've ever tracked, and the vast cloud of icy debris surrounding all of it, could fit across the width of the Milky Way, somewhere on the order of 40,000 to 50,000 times over. Our solar system isn't just small compared to the galaxy. It's small enough that tens of thousands of solar systems, laid end to end, would be needed just to span the galaxy once. And the galaxy that our tiny 2 light-year solar system sits inside of, that roughly 100,000 light-year wide structure containing up to 400 billion stars, is itself just one of somewhere between a few hundred billion and 2 trillion galaxies, by current, still debated estimates, inside an observable universe that's 93 billion light-years across. And even that entire observable universe might only be a small fraction of a universe that could, for all we currently know, be infinite. So let's go back to where we started, because now all of these numbers can actually sit next to each other properly. You live on a planet that orbits a star. That star, along with everything else in our solar system, out to the far edge of the Oort cloud, occupies a region of space roughly 2 light-years across. That entire solar system sits inside a galaxy that is, by the most common measurements, about 100,000 light-years across, though depending on exactly how you define its edge, that figure could reasonably run anywhere from around 87,000 light-years up to 200,000 light-years. Somewhere between 100 billion and 400 billion stars share that galaxy with our Sun, and nobody has ever managed to count them precisely, because most of them are simply too faint to see. Our Sun sits roughly 26,000 to 30,000 light-years out from the galactic center, inside a minor structural feature called the Orion Arm, orbiting a supermassive black hole with the mass of 4 million suns, a black hole humanity only managed to photograph directly for the first time in May of 2022. It takes the Sun somewhere between 225 and 250 million years to complete one single orbit around that black hole, even while traveling at roughly 500,000 miles per hour. Since the solar system formed, it has completed only about 20 of those orbits. Zoom out past our own galaxy, and you reach Andromeda, 2.5 million light-years away, a galaxy roughly twice our size that we only confirmed was a separate galaxy at all in 1923, when Edwin Hubble spotted a single flickering star on a photographic plate and realized the object it belonged to was much too far away to be part of our own Milky Way. Before that discovery, some of the most respected astronomers in the world genuinely believed the Milky Way was the entire universe. It took less than 5 years and one Cepheid variable star to prove them wrong. Zoom out again, past Andromeda, past the roughly 50 dwarf galaxies of our local group, past the 110 million light-year Virgo supercluster, and you land inside Laniakea, a supercluster spanning roughly 500 million light-years and containing on the order of 100,000 galaxies, a structure so large it wasn't even properly identified and named until 2014, and one that, we now know, isn't even permanently held together, destined to eventually drift apart as the universe keeps expanding. And Laniakea itself is just one structure among an unknown number of others, inside an observable universe roughly 93 billion light-years across, that may contain anywhere from a few hundred billion to 2 trillion galaxies, depending on which recent study you trust, inside a universe whose true full size, beyond what we can currently observe, remains completely unknown and might not have any size limit at all. That's the actual scale of the galaxy you live in, and the universe that galaxy sits inside of. Not a metaphor, not a rounded-off estimate designed to sound impressive. Those are the real numbers, drawn straight from NASA, from Nobel Prize-winning research, from peer-reviewed astronomy, and from the astronomers who are still, right now, arguing with each other over exactly how many billion galaxies actually exist. You already knew space was big. Most people do. But there's a difference between knowing that in the abstract and actually walking through the numbers, layer by layer, solar system, galaxy, supercluster, observable universe, and watching just how quickly each layer swallows the one before it whole. The next time you look up at that pale band of light stretching across the night sky, the one the ancient Greeks first guessed was made of individual stars, remember that you're looking at only the tiniest, nearest sliver of a structure that is, by every measurement we currently have, functionally too large for the human mind to actually picture all at once. We can only get close, and honestly, close is still enough to make you feel very, very small. Before we wrap this up, it's worth taking a step back and looking at how astronomers actually manage to measure any of this in the first place, because the tools involved are almost as remarkable as the numbers they produce. The most basic of those tools, and the foundation everything else in this video is ultimately built on top of, is a technique called parallax, and you can actually demonstrate the core idea yourself without any equipment at all. Hold a finger up in front of your face, close one eye, then switch to the other eye, and watch how your finger appears to jump slightly against the background behind it. That apparent shift happens because you're viewing your finger from two slightly different positions, your two eyes, and the closer the finger is to your face, the bigger that apparent jump appears. Astronomers use exactly the same principle on a vastly larger scale. Instead of two eyes, they use Earth's own orbit around the Sun, observing a nearby star's position once, then again 6 months later from the opposite side of that orbit, roughly 186 million miles away from the first observation point. Nearby stars appear to shift very slightly against the background of much more distant stars, and the size of that shift, measured in a unit of angle called an arcsecond, or fractions of one, directly reveals the star's distance through simple geometry. It's the same trick as your finger and your two eyes, just using the width of Earth's entire orbit as the gap between viewpoints instead of the few inches between your eyeballs. Parallax is by far the most direct and reliable distance measuring technique astronomers have, the base of the entire cosmic distance ladder that every other method, including Leavitt's Cepheid technique, is ultimately calibrated against. But it only works for relatively nearby stars, because the farther away a star sits, the smaller its parallax shift becomes, and at some point, the shift gets too tiny to measure at all. The European Space Agency's earlier Hipparcos satellite, active from 1989 to 1993, managed to measure parallax distances for about 118,000 stars, reaching out to roughly 1,600 light-years, which sounds like a lot, until you remember that's only a little more than 1% of the Milky Way's full diameter. Gaia, the same mission responsible for that billion-star map of the galaxy, pushed the technique dramatically further, measuring angles as small as 20 to 25 microarcseconds, an angle the European Space Agency compares to being able to measure the width of a single human hair from 1,000 kilometers away. That level of precision let Gaia extend reliable parallax measurements out to roughly 30,000 light-years in some cases, still nowhere near the full width of the galaxy, but a massive leap beyond what was possible before it. This is the honest reason so many of the figures in this video come with a range instead of one clean number. Parallax, the most trustworthy distance tool we have, only reaches a fraction of the way across our own galaxy before it runs out of precision. Everything beyond that range, the far side of the Milky Way, Andromeda, Laniakea, the observable universe itself, has to be measured using less direct, more heavily modeled techniques, Cepheid variables, redshift, standard candles, calibrated against parallax at the near end, and extrapolated outward from there. Every layer of distance in this video is built on the layer beneath it, and every layer adds a little more uncertainty than the one before, which is exactly why the numbers get fuzzier the farther out you go. Nearly every distance figure in this video, the size of the Milky Way, the distance to Andromeda, the width of Laniakea, traces back to the same basic technique, the standard candle. A standard candle is any object whose true brightness astronomers already know, which means that by comparing how bright it actually is to how dim it appears from Earth, they can calculate exactly how far away it must be. Cepheid variable stars are the classic example, and the reason they work as standard candles comes down to a relationship discovered in 1912 by astronomer Henrietta Leavitt. Leavitt noticed that Cepheid stars in the Magellanic Clouds pulsed, brightening and dimming, at rates directly tied to how luminous they actually were. The slower the pulse, the brighter the star's true output. Once you know a Cepheid's pulse rate, you know its real brightness. And once you know its real brightness compared to how faint it looks from here, basic physics tells you the distance. That single relationship is the reason Harlow Shapley could map the size of the Milky Way in 1918. It's the same relationship Edwin Hubble used in 1923 to prove Andromeda was millions of light-years away, not a nearby cloud of gas. It's a tool built by one astronomer, used by two others to overturn humanity's entire understanding of the universe within about a decade, and it's still one of the foundational techniques astronomers rely on today. Measuring something like Sagittarius A, on the other hand, required a completely different method because you can't see a black hole directly. By definition, no light escapes it. Instead, Reinhard Genzel's and Andrea Gheze's teams tracked the motion of visible stars orbiting something invisible at the galactic center, applying the same basic orbital mechanics that let you calculate the sun's mass just by watching how fast the planets orbit it. Watch something orbit an invisible point closely enough, for long enough, and you can calculate the mass of whatever's sitting at that point, even though you'll never see it directly. That's how we know Sagittarius A weighs about 4 million suns, decades before anyone actually managed to photograph its shadow in 2022. And measuring the size of the observable universe itself relies on yet another set of tools entirely. Tracking the redshift of light from extremely distant galaxies, essentially measuring how much the wavelength of that light has been stretched by the expansion of space during its journey toward us, combined with careful modeling of how that expansion has behaved since the Big Bang. It's this method that produces the sometimes confusing result that the observable universe is 93 billion light-years across, even though it's only 13.8 billion years old, because the modeling accounts for space itself stretching during the light's travel time, not just the light's raw travel time on its own. Every single number in this video, the 100,000 light-year width of our galaxy, the 4 million solar mass black hole at its center, the 2.5 million light-year gap to Andromeda, the 93 billion light-year width of the observable universe, is the product of decades, in some cases over a century, of careful incremental scientific work, building one measurement on top of the next. Leavitt's Cepheid relationship enabled Shapley's galaxy measurement. Shapley's work gave Hubble the tool he needed to measure Andromeda. Hubble's discovery reshaped our entire picture of the universe, which every subsequent generation of astronomers has continued to refine, correct, and in some cases, completely overturn, right up through the 2025 research that turned the certain Andromeda collision into a 50-50 coin flip, and the ongoing argument over whether there are a few 100 billion or 2 trillion galaxies out there. That's really the last thing worth sitting with here. This isn't a settled body of knowledge that got written down once and closed. It's a living, ongoing argument, conducted by thousands of scientists, using ever-improving instruments, constantly revising numbers that were once treated as fixed facts. The Milky Way's size has a range instead of one number because our measurement methods still disagree at the margins. The star count has a range because most stars are still too faint to individually count. The Andromeda collision went from certain to 50-50 because someone ran a better simulation with better data. Even the number of galaxies in the universe swung by a factor of 10 and then partway back again within the last decade. We are, all of us, watching this map get redrawn in real time, and every redraw makes the picture a little more accurate and, if anything, makes the true scale of everything look even larger than the version we grew up believing. There's a piece of this story we haven't touched yet, and it changes the weight of almost every number we've already covered. Most of the Milky Way isn't actually made of anything we can see. That idea traces back to 1933, when Swiss astronomer Fritz Zwicky was studying the Coma cluster, a collection of roughly 1,000 galaxies bound together by gravity. Zwicky noticed something that didn't add up. The cluster's galaxies were moving so fast that the whole structure should have flown apart, torn loose by its own velocity, unless there was far more mass holding it together than anyone could actually see through a telescope. Zwicky proposed that some kind of invisible material, what he called Dunkel Materie, dark matter in German, had to be filling the gaps. Almost nobody believed him. Astrophysicist Netta Bachkohl of Princeton has described the idea as having been too outrageous to believe for almost 4 decades. That changed in the 1970s, largely through the work of astronomer Vera Rubin, working alongside collaborator Kent Ford. Rubin studied something called rotation curves, essentially a graph of how fast stars orbit at different distances from a galaxy's center. Basic physics says that stars farther from a galaxy's center, out where there's less visible matter to hold them in, should orbit more slowly, the same way outer planets in our own solar system move more slowly than inner ones. Rubin's first major target, in a 1970 paper written with Ford, was our neighbor Andromeda. Instead of the expected downward slope showing outer stars moving slower, the graph came back essentially flat. Stars far out at the edge of Andromeda were orbiting just as fast as stars much closer to its center. Between 1976 and 1986, Rubin and Ford expanded the survey to more than 75 spiral galaxies. Every single one showed the same flat curve. Something invisible, spread out in a vast halo well beyond the visible edge of each galaxy, had to be providing the extra gravity needed to hold those fast-moving outer stars in their orbits. By the early 1980s, dark matter had gone from a forgotten, borderline crackpot idea to one of the central pillars of modern astrophysics. It still hasn't been directly detected, not once, by any instrument on Earth or in space. Everything we know about it comes from its gravitational fingerprints, the same basic principle that let astronomers calculate the mass of Sagittarius A without ever seeing it directly. Here's where this connects back to the Milky Way itself. Because we live inside our own galaxy, astronomers can't simply point a telescope at it and measure its outline the way they can with a distant galaxy like Andromeda. Weighing our own galaxy, dark matter included, has been a genuinely difficult problem, and the published estimates reflect that difficulty. For years, credible estimates for the Milky Way's total mass ranged anywhere from about 500 billion to as much as 3 trillion solar masses, an enormous span, driven almost entirely by how differently various research teams modeled the galaxy's invisible dark matter halo. A widely cited 2019 study, combining data from the Hubble Space Telescope and the European Space Agency's Gaia satellite, led by researchers including Laura Watkins at the European Southern Observatory, tracked the motion of globular star clusters orbiting the Milky Way at great distances, since the speed of those clusters reveals how much gravity, and therefore how much mass, is pulling on them. That study landed on a figure of approximately 1.5 trillion solar masses, within a radius of about 129,000 light-years from the galactic center. A separate estimate, using the motion of so-called hypervelocity stars, stars flung outward at extreme speeds by interactions near the central black hole, produced a figure between 1.2 and 1.9 trillion solar masses, broadly consistent with the Hubble Gaia result. More recent modeling work has produced figures both somewhat higher and somewhat lower than that 1.5 trillion mark, depending on the specific dark matter distribution assumed, underscoring, again, that this is a number still being actively refined rather than a fixed constant. And here's the detail that puts the rest of this video in a completely different light. According to the researchers behind that 1.5 trillion solar mass estimate, only a small percentage, a few percent at most, of the Milky Way's total mass is actually made up of its 100 to 400 billion visible stars. The rest, somewhere around 90% of the entire galaxy by mass, is dark matter, invisible, undetected directly by any instrument, known only because of how it bends the paths of the stars and gas we can see. So every number we've covered so far, the 100,000 light-year width, the hundreds of billions of stars, the 4 million solar mass black hole at the center, describes only the visible sliver of a galaxy that is, by mass, almost entirely something we still can't directly detect. We don't just live in a galaxy that's almost incomprehensibly large. We live in a galaxy where the part we can actually see and count and photograph is, by weight, a rounding error next to the part we can't. Let's go back to the woman whose work made almost every distance measurement in this video possible in the first place, because her own story is a smaller scale version of the same theme: real, foundational discovery, made from a position most people would never think to look for it. Henrietta Swan Leavitt was born in 1868 and began working at the Harvard College Observatory in 1893, first as a volunteer, and from 1902 onward in a paid position. Leavitt was one of a group of women employed at Harvard as computers, a job title that meant exactly what it sounds like: manually extracting data, measurements, magnitudes, positions, from thousands of photographic plates of the night sky. These women were paid between 25 and 30 cents an hour for work that would eventually reshape humanity's understanding of the size of the universe. Leavitt's specific assignment was to study variable stars, stars whose brightness rises and falls over time, using photographic plates that captured the Magellanic Clouds, two small satellite galaxies visible from the southern hemisphere. By 1907, Leavitt had already published a catalogue of 1,777 variable stars she'd identified in the Magellanic Clouds. But it was her 1912 paper, titled Periods of 25 Variable Stars in the Small Magellanic Cloud, that changed everything. Leavitt focused specifically on Cepheid variables, and she made a key simplifying assumption. Since all the stars she was studying sat within the same small, distant satellite galaxy, they were all, for practical purposes, roughly the same distance from Earth. That meant any difference in how bright they appeared had to come from a difference in how bright they actually were, not from some being closer and others farther away. When she plotted each star's brightness against how long its pulsing cycle took, a clear pattern emerged. The longer a Cepheid's period, the brighter it actually was. As she put it in her own 1912 publication, there is a simple relation between the brightness of the variables and their periods. That relationship became known as the Leavitt law, and it gave astronomers their first true standard candle, a way to look at a Cepheid variable anywhere in the universe, measure how long its brightness cycle takes, calculate how bright it actually must be, and then compare that to how dim it appears from Earth to calculate exactly how far away it is. It's worth pausing on what happened next, because it's not a small footnote. Leavitt's discovery was published in a 1912 Harvard Observatory circular under the name of Edward Pickering, the observatory's director, with Leavitt credited only as the person who had prepared the statement. Pickering's eventual successor at the observatory was Harlow Shapley, the same astronomer who, just a few years later, used Leavitt's period luminosity relationship to measure the size of the Milky Way for the first time, and the same astronomer who would go on to lose the great debate to Edwin Hubble, who used that same relationship again to prove Andromeda was a separate galaxy entirely. Every major distance measurement in the story we've told so far, Shapley's map of the Milky Way, Hubble's measurement of Andromeda, runs directly back through a discovery made by a woman working for a fraction of $1 an hour, cataloging faint smudges of light on glass photographic plates, whose name most people watching this video have probably never heard before today. Leavitt died in 1921, 2 years before Hubble's discovery at Andromeda, and never lived to see her period luminosity relationship become the tool that finally proved the universe was bigger than one galaxy. Since Leavitt, Shapley, and Hubble first mapped the broad outlines of the Milky Way, the tools for measuring our own galaxy from the inside have only gotten sharper, and one modern mission in particular deserves mention here: the European Space Agency's Gaia spacecraft. Gaia launched on December 19, 2013, and was positioned at a gravitationally stable point in space called L2, about 1 million miles from Earth, where it could scan the sky without our planet blocking its view. Its mission was to build the most precise three-dimensional map of the Milky Way ever attempted, and it delivered. Gaia's first major data release, in 2016, pinned down the position and brightness of 1.142 billion stars. A later release, in 2018, refined that to nearly 1.7 billion stars, complete with distance and motion data for each one. By the time the mission concluded its observations in January 2025, Gaia had made more than 3 trillion individual observations, covering roughly 2 billion stars and other objects throughout the Milky Way and beyond, tracking their motions, temperatures, and composition with a level of precision no previous survey had come close to matching. Even so, and this is worth sitting with, all of that data, more than 3 trillion observations, 2 billion individually tracked stars, still amounts to roughly 1 to 2% of the total estimated star population of our own galaxy. Gaia produced the richest map of the Milky Way in human history, and it still only managed to directly chart a small fraction of the galaxy we actually live inside. While Gaia was busy remapping the galaxy from orbit, ground-based and infrared surveys were busy rewriting one of the more basic facts about the galaxy's shape: how many spiral arms it actually has. For decades, going back to radio observations in the 1950s, the standard picture of the Milky Way included 4 major spiral arms, named Norma, Scutum Centaurus, Sagittarius, and Perseus, all winding outward from the galaxy's central bar. Then, in 2008, NASA's Spitzer Space Telescope completed an infrared survey of the galactic plane, covering 800,000 individual images and more than 110 million stars. Astronomer Robert Benjamin and his team at the University of Wisconsin used that data to count star densities in the direction of each expected arm, and the results upended the standard picture. The Scutum Centaurus and Perseus arms showed up clearly, exactly the star density spike you'd expect from a major spiral arm. But looking toward where the Sagittarius and Norma arms were supposed to be, there was no comparable jump in star counts at all. Benjamin's conclusion, presented at a 2008 meeting of the American Astronomical Society, was that the Milky Way likely had only 2 major arms, not 4, with Sagittarius and Norma effectively demoted to minor structures similar to our own Orion spur, arms defined more by gas and pockets of star formation than by a dense population of stars. That wasn't the end of the story either. Later surveys, including a detailed 2019 study led by astronomer James Urquhart using a 3-dimensional map of 1,650 massive young stars, found evidence that the 2 missing arms hadn't vanished after all, just that they were harder to detect using the star-counting method Spitzer relied on. Urquhart's data showed all 4 arms clearly, with the Sagittarius arm actually appearing more prominently in that particular survey than the better-known Perseus arm. Benjamin himself, reflecting on the ongoing revisions to the Milky Way's map, offered a comparison that fits neatly into everything else in this video. We will keep revising our picture in the same way that early explorers sailing around the globe had to keep revising their maps. We live inside the very structure we're trying to map, and every new instrument, Spitzer's infrared camera, Gaia's billion-star census, the Event Horizon Telescope's radio dishes, keeps redrawing the shape of the home we've lived in the entire time. Let's bring this back down to something you can actually go outside and check for yourself tonight, weather permitting, and look at how much of any of this you can actually see with your own 2 eyes, no telescope required. The honest answer is, not much, relatively speaking, but more than most people assume. Astronomers using the standard measure of stellar magnitude, brightness as seen from Earth, calculate that there are 9,096 individual stars bright enough to be visible to the naked eye across the entire sky, counting both hemispheres together, a figure drawn from the Yale Bright Star Catalogue, which lists 9,110 stars meeting that same naked eye threshold. That magnitude system itself is ancient, tracing back to the Greek astronomer Hipparchus, who first ranked visible stars by brightness more than 2,000 years ago, and whose basic scale, refined and mathematically formalized over the centuries since, is still the exact system astronomers use today to decide which stars belong on that list of 9,096. Since you can only ever see one hemisphere of sky from any single point on Earth at any given time, that number roughly splits in half, down to about 4,548 stars, theoretically visible from wherever you happen to be standing. Factor in that roughly half of Earth is always in daylight, that stars near the horizon get dimmed by atmospheric extinction, and that even a small amount of light pollution cuts the visible count dramatically, down to somewhere around 1,000 stars from a suburban sky, maybe under a few hundred from a typical city, and the realistic number of individual stars you could point to and identify on any given clear night, even under excellent rural conditions, lands closer to 2,000 or 3,000. Every one of those points of light is an individual star inside our own galaxy, a tiny, local sample pulled from a population of 100 to 400 billion, the overwhelming majority of which no human eye and no telescope built so far has ever managed to see individually at all. There's exactly one object visible to the naked eye that isn't part of our own galaxy at all, and we've already spent a fair amount of time discussing it: Andromeda. At an apparent magnitude of about 3.1, Andromeda is faint but genuinely visible without any equipment, even from areas with moderate light pollution, if you know exactly where to look. It holds the distinction of being the single most distant object the unaided human eye can detect, a smudge of light that is, in reality, an entire galaxy roughly twice the size of our own, sitting 2.5 million light-years away. Long before Edwin Hubble proved what Andromeda actually was, people had already been looking directly at it for centuries, without any idea what they were seeing. The earliest known written record of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi, who included it in his Book of Fixed Stars, completed around the year 964 CE. Al-Sufi, working from an observatory in Shiraz under the patronage of the Buyid ruler Adud al-Dawla, described the object simply as al-Latha al-Sahabiyya, commonly translated as the little cloud or the nebulous smear, referencing nothing more than its faint, smudgy appearance to the naked eye. He had, of course, no way of knowing that his little cloud was actually a separate galaxy containing roughly 1 trillion stars, sitting 2.5 million light-years from where he stood. Interestingly, no Greek astronomer, including Ptolemy, whose star catalogue Al-Sufi was revising and correcting, ever recorded it at all. Andromeda wouldn't be observed through a telescope for the first time until 1612, and even then, astronomers spent centuries afterward classifying it as a nebula, a cloud of gas and dust presumed to sit within our own galaxy, right up until Hubble's 1923 discovery finally proved otherwise. So the next clear night you get the chance, look up, find that faint smudge near the constellation Andromeda if your sky is dark enough, and know that you're looking at the same object a Persian astronomer wrote about more than 1,000 years ago, the same object multiple generations of astronomers mistook for a nearby gas cloud, and the same object that, once properly measured with a tool built from the work of an underpaid Harvard computer, finally proved to everyone that the Milky Way was never the whole universe to begin with. Edwin Hubble's Cepheid discovery at Andromeda in 1923 turned out to be only the first of 2 discoveries that would carry his name into the history books, and the second one is arguably even bigger than the first. Once Hubble had established that Andromeda and other similar spiral nebulae were separate galaxies entirely, he turned to a broader question, looking at how all these other galaxies were actually moving. Working from measurements of galactic redshift, a stretching of a galaxy's light toward the red end of the spectrum that happens when an object is moving away from the observer, originally gathered by astronomer Vesto Slipher, the same person who had predicted Andromeda's approach decades earlier, Hubble compared each galaxy's redshift to its distance, distances he calculated using the same Cepheid method built on Henrietta Leavitt's original discovery. On March 15, 1929, Hubble published a short paper in the Proceedings of the National Academy of Sciences titled A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae. In it, he laid out the evidence for what became known as Hubble's law. The farther away a galaxy is, the faster it appears to be receding from us. Hubble's original 1929 paper plotted the velocities and distances of 24 nebulae, and even with just 24 data points, the pattern was already strikingly linear. The implication was almost too large to process at the time. If every distant galaxy is moving away from us, and the farther ones are moving away faster, then the universe itself isn't static, it's expanding, uniformly, in every direction. Historical accounts describe Albert Einstein as elated when he heard about Hubble's results. Einstein's own equations for general relativity had actually predicted an expanding or contracting universe years earlier, but Einstein himself had rejected that implication, adding a term to his equations specifically to force the math to describe a static, unchanging universe instead, since a static universe matched the prevailing assumption of the time. After Hubble's evidence came in, Einstein reportedly abandoned that fix and later referred to it as his greatest blunder. It's worth noting, for the sake of accuracy, that Hubble's own original distance measurements in that 1929 paper were later found to be off by a significant margin, roughly a factor of 7 too small, due to calibration issues with the standard candles used at the time, meaning his original estimate of the universe's expansion rate was considerably too high. But the fundamental relationship he identified, that recession velocity scales with distance, held up completely once the calibration was corrected, and it remains one of the central pillars of modern cosmology. It's also worth noting, in the interest of full accuracy, that historians of science have pointed out Hubble wasn't working in isolation. Astronomer Georges Lemaitre had derived a very similar distance-velocity relationship 2 years earlier, in 1927, using redshift data gathered by SLIFR and apparent brightness data from Hubble himself. Though Lemaitre's paper, published in a lesser-known Belgian journal, went largely unnoticed at the time. Today the relationship is officially known by formal astronomical convention as the Hubble-Lemaitre law, acknowledging both contributions. So within the span of about 6 years, from 1923 to 1929, one astronomer working at one observatory in California fundamentally rewrote humanity's picture of the universe twice over. First by proving the Milky Way wasn't alone, and then by proving that everything beyond it was actively rushing apart. Between Leavitt's period luminosity relationship in 1912, Shapley's Milky Way measurement in 1918, Hubble's Andromeda discovery in 1923, and Hubble's expansion discovery in 1929, the entire modern picture of an expanding universe filled with billions of separate galaxies was assembled in less than 2 decades, built almost entirely on the careful measurement of flickering stars on glass photographic plates. That expanding universe hasn't stopped revealing surprises, and one of the biggest ones is happening right now, with an instrument that only started collecting data in the summer of 2022, the James Webb Space Telescope. Where Hubble's telescope and its various successors had already pushed the boundary of the observable universe back to galaxies existing a few 100 million years after the Big Bang, JUIC's infrared instruments were specifically designed to peer even farther back, into a period astronomers call cosmic dawn, when the very first stars and galaxies were assembling out of raw hydrogen and helium. In May 2024, a team working on the JAST Advanced Deep Extragalactic Survey, known as JADES, announced the discovery of a galaxy named JADES GS Z14-0, confirmed spectroscopically at a redshift of 14.32. That redshift places the galaxy at a point in time just 290 to 300 million years after the Big Bang, meaning its light has been traveling toward Earth for roughly 13.5 billion years. At the time, it broke the previous distance record, held by a galaxy called JADES GS Z13-0, by shattering through what researchers had assumed was close to the practical limit of what the telescope could detect. Astronomer Kevin Hainline of the University of Arizona described the discovery as one of the strangest moments of his career, and colleague George Riquet put it more bluntly: nobody dreamed that there would be galaxies this bright at this high redshift. Despite existing so early in the universe's history, JADES GS Z14 Psi measures more than 1,600 light-years across and is bright enough that researchers had to rule out the possibility that its light was being powered by a feeding supermassive black hole. Instead, the brightness appears to come from an unexpectedly large and active population of young stars, suggesting massive galaxies assembled themselves far faster in the early universe than existing models predicted. That record didn't last. Astronomers, including Yale professor Peter van Dokkum, have since identified an even more distant galaxy, informally referred to as MOM Z14, with a redshift of 14.44, corresponding to a galaxy that existed when the universe itself was only about 280 million years old, roughly 2% of its current age. Van Dokkum offered a comparison that puts the sheer age involved into perspective. Sharks, as a species, have existed on Earth for a longer stretch of time than the gap between the Big Bang and this galaxy's formation. As Van Dokkum told one interviewer, discoveries like this happen periodically, and each one is, in his words, cause for pause and reflection. Researchers on the JADES team have been direct about what this means going forward. Given how small a slice of sky they search to find these record-breaking galaxies, it's likely that even more distant, even earlier galaxies remain to be found as the James Webb Space Telescope continues its survey work. It's a fitting, ongoing coda to everything we've covered in this video. The observable universe isn't just large, its edges keep receding, quite literally, every time a more powerful instrument comes online. Hubble pushed that edge back with a 100-inch mirror and photographic plates in the 1920s. The Hubble Space Telescope pushed it back again in the 1990s and 2000s. And right now, in the current decade, the James Webb Space Telescope is pushing it back roughly to the very edge of when galaxies could have existed at all, closing in on the Big Bang itself, one redshift record at a time. Before we get to what the Milky Way has been eating, it's worth answering a more basic question we've been dancing around this whole video. The question of what actually makes a galaxy look like ours, as opposed to something else entirely, out of the hundreds of billions of galaxies we've been discussing. The answer traces back to Edwin Hubble again, the same astronomer responsible for both major discoveries we've already covered. In 1926, and later in more complete form in his 1936 book, The Realm of the Nebulae, Hubble developed a classification system for sorting galaxies by their visual shape, a system still taught and used by astronomers today, commonly known as the Hubble tuning fork, because of the shape of the diagram used to illustrate it. On one side of the fork sit elliptical galaxies, round or oval-shaped collections of stars with no spiral arms and no disk structure, classified on a scale from E0, nearly circular, to E7, highly elongated. Elliptical galaxies tend to be made up of older, redder stars, and giant ellipticals are often found sitting at the very center of large galaxy clusters. On the other side of the fork sit spiral galaxies, further divided into ordinary spirals and barred spirals, our own Milky Way's category, distinguished by whether or not a straight bar-shaped structure of stars runs through the galaxy's central bulge before the arms curl outward. Spirals are further labeled A through C, depending on how tightly their arms are wound and how large their central bulge is. An SSA, or SPI galaxy, has a big bulge and tightly wound arms, while an SC, or SBC galaxy, has a small bulge and loosely wound, sprawling arms. Sitting at the junction between the two branches of the fork are lenticular, or S0, galaxies, disc-shaped like spirals, but lacking visible spiral arms, considered a transitional form between the two main types. And outside the fork entirely sit irregular galaxies, objects with no clean symmetrical structure at all, frequently the result of a galaxy colliding with, or being gravitationally disrupted by, another one nearby, a category that, fittingly enough, includes both of the Magellanic Clouds. Hubble originally believed, incorrectly as it turned out, that this diagram represented an evolutionary sequence, that galaxies actually transformed from one shape into another as they aged, starting as ellipticals and evolving into spirals over time. Later research disproved that idea. Elliptical galaxies and spiral galaxies rotate in fundamentally different ways, and there's no physical mechanism by which a slowly rotating elliptical galaxy could spontaneously start spinning fast enough to develop spiral arms. But even stripped of its original incorrect evolutionary theory, Hubble's classification system turned out to be genuinely useful, and it's still the basic vocabulary astronomers reach for anytime they need to describe a galaxy's shape. Our own Milky Way is classified as a barred spiral, specifically somewhere in the SBB to SBC range, meaning a moderate to small central bulge and moderately loose spiral arms, the same broad category as roughly 2 out of every 3 spiral galaxies observed in the nearby universe. We're not a strange outlier shape-wise. We're a fairly typical example of the single most common structural category of large galaxy in the observable universe, sitting inside a system of classification invented by the same person who first proved we weren't the only galaxy at all. There's one more piece of the neighborhood worth walking through before we close, because it turns out the Milky Way hasn't just been sitting quietly in place for billions of years, minding its own business. It's been eating. Start with 2 small, ragged patches of light, visible only from the southern hemisphere, the large and small Magellanic Clouds. They were named after the Portuguese explorer Ferdinand Magellan, whose crew documented them during their circumnavigation voyage in the early 1500s, though sources note that indigenous peoples across the southern hemisphere had been aware of these 2 hazy smudges in the sky for a very long time before any European ever wrote them down. The large Magellanic Cloud, the bigger and closer of the pair, sits roughly 160,000 to 163,000 light-years from Earth, and stretches about 14,000 to 32,000 light-years across, depending on which measurement boundary you use, with an estimated 20 to 30 billion stars of its own. The small Magellanic Cloud sits farther out, at roughly 190,000 to 200,000 light-years, and is smaller still, home to a few 100 million to a few billion stars across a diameter of around 7,000 to 19,000 light-years. Together, they rank as the fourth largest galaxy system in the local group, after Andromeda, the Milky Way, and the Triangulum Galaxy, and they're bright enough to be visible to the naked eye, making them, alongside Andromeda, among the only external galaxies most people could ever point to directly in the night sky without any equipment at all. Both Magellanic Clouds are classified as dwarf galaxies and satellite galaxies of the Milky Way, meaning they're gravitationally caught in an ongoing, slow-motion orbit around us. And ongoing is doing real work in that sentence, because current research suggests both clouds, particularly the Large Magellanic Cloud, are gradually spiraling inward, falling toward an eventual merger with our own galaxy over the coming billions of years, following essentially the same physics driving the, now less certain, Andromeda scenario, just on a much smaller and much more local scale, and with much smaller galaxies being consumed rather than two roughly equal giants colliding. That process of one galaxy slowly devouring a smaller one isn't hypothetical or purely future tense for the Milky Way. It's something we have direct, ongoing evidence of happening right now, and something we can trace happening in the past. The clearest present-day example is a structure called the Sagittarius Dwarf Spheroidal Galaxy, a small satellite galaxy that the Milky Way has been actively tearing apart for billions of years. It has already plunged directly through our galaxy's disk multiple times, and each pass strips away more of its stars, flinging them out into long, looping streams of debris that wrap entirely around the Milky Way in ribbon-like arcs, still visible today to astronomers mapping the galaxy's outer halo. It's not a metaphor to say the Sagittarius dwarf is being eaten. It's a direct, observable, ongoing process, one small galaxy's stars being gradually stripped away and absorbed into our own with every orbit. Further back in time, there's an even bigger example, discovered only within the last several years, entirely through data gathered by the European Space Agency's Gaia mission. Around 8 to 11 billion years ago, astronomers now believe, the young Milky Way collided with a substantial dwarf galaxy, one holding a total mass more than 10 billion times that of our Sun, in what researchers now call the Gaia-Enceladus merger, or more informally, the Gaia sausage. That second, stranger nickname comes directly from how the collision's leftover stars showed up in the data. When Cambridge astronomer Vasily Belokurov and his colleagues plotted the velocities of ancient stars in the Milky Way's halo, tens of thousands of them fell into a distinctive, elongated, sausage-shaped pattern on the graph, evidence that they were all thrown onto similar long, stretched, needle-like orbits by one single, catastrophic, head-on collision billions of years ago. Belokurov described the impact plainly. The collision ripped the dwarf to shreds, leaving its stars moving in very radial orbits that are long and narrow like needles. That ancient merger is now believed to have fundamentally reshaped the young Milky Way, puffing up its thick stellar disk, triggering a burst of new star formation, and contributing roughly half of all the stars found in the galaxy's halo today. Later research, including a 2026 study, has gone even further, suggesting the collision may have entirely erased evidence of whatever rotating disk the Milky Way had before the impact, meaning the point astronomers previously identified as when the galaxy's disk formed might actually mark something different, the moment the galaxy finished recovering from getting hit. Put simply, a meaningful fraction of the stars currently sitting in the Milky Way's halo, quite possibly including some of the older stars orbiting relatively near our own Sun, aren't originally from the Milky Way at all. They're leftover debris from another galaxy entirely, one that existed billions of years ago, got torn apart in a head-on collision, and was slowly absorbed into the structure we now call home. Whatever this galaxy is, at some level, a genuinely significant part of it used to be something else. There's one more discovery worth including here, because it's the closest thing science has to direct physical proof that the Big Bang itself actually happened, and it was found entirely by accident. In 1964 and 1965, two radio astronomers at Bell Labs in Holmdel, New Jersey, Arno Penzias and Robert Wilson, were using a large horn-shaped antenna, originally built for early satellite communication, to study radio emissions from the Milky Way. No matter what they did, they kept picking up a faint, persistent hiss of background noise, coming uniformly from every direction in the sky, at every time of day, in every season. They assumed it had to be some flaw in their equipment. They checked the wiring. They ruled out interference from nearby New York City. At one point, they even found a pair of pigeons nesting inside the antenna and had to physically clean out the accumulated droppings, on the reasonable suspicion that it might be causing the interference. None of it made the signal go away. As it turned out, Penzias and Wilson weren't picking up equipment noise at all. Completely unknown to them, physicists at nearby Princeton University, led by Robert Dick along with Jim Peebles and others, had independently been developing a theoretical prediction that if the universe really had begun in a hot, dense Big Bang, it should have left behind a faint, uniform bath of leftover radiation, cooled by billions of years of cosmic expansion down to just a few degrees above absolute zero, still detectable today, coming equally from every direction in the sky. When the two groups connected, the match was immediate. What Penzias and Wilson had stumbled onto, purely as an unwanted noise problem in a satellite antenna, was the cosmic microwave background, the actual, physical afterglow of the Big Bang itself, light that has been traveling through an expanding universe for nearly 13.8 billion years, redshifted all the way down from visible light into the microwave range along the way. It remains, to this day, one of the strongest pieces of direct physical evidence that the universe really did begin in an event like the one Hubble's redshift measurements first pointed toward back in 1929. Penzias and Wilson received the Nobel Prize in Physics for the discovery in 1978. That faint, accidental hiss from a New Jersey antenna eventually became one of the most precisely studied signals in all of science. Multiple dedicated space telescopes have been built specifically to map it in ever finer detail, and the most recent of them, the European Space Agency's Planck satellite, collected data from 2009 to 2013 before releasing what remains, to date, the most detailed all-sky map of the cosmic microwave background ever produced, a snapshot of light emitted when the universe itself was only about 380,000 years old. By carefully measuring the tiny temperature fluctuations in that ancient light, fluctuations smaller than a millionth of a degree, Planck's team was able to calculate the universe's age with remarkable precision, landing on a final figure of roughly 13.8 billion years, specifically 13.813 billion years, with an uncertainty of only about 38 million years, in the mission's final 2015 data release. Planck's data also pinned down the universe's basic composition with a precision no previous mission had matched. Roughly 4.9% ordinary matter, the stuff that makes up stars, planets, and everything we can directly see or touch. Roughly 26.8% dark matter, the same invisible material Vera Rubin's rotation curves first pointed toward decades earlier, and roughly 68.3% dark energy, a mysterious force believed to be driving the accelerating expansion of the universe itself, a component astronomers still don't fully understand even now. Put plainly, according to our best current measurements, the ordinary matter the Earth, the Sun, and every star in the Milky Way are made of accounts for less than 5% of everything that exists. That third ingredient, dark energy, is its own separate story, and a fairly recent one. In 1998, two competing research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and featuring Adam Rees as lead author on the team's key paper, were independently using distant exploding stars called Type Ia supernovae as standard candles, in essentially the same tradition as Leavitt's Cepheids, to measure how the universe's expansion rate had changed over billions of years. Both teams expected to find the expansion gradually slowing down, dragged on by the combined gravity of all the matter in the universe. Instead, both teams found the opposite. The expansion was speeding up. That completely unexpected result implied the existence of some kind of mysterious, uniformly distributed force actively pushing space apart, a force with no known source, now simply labeled dark energy. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for the discovery. And dark energy, whatever it actually is, remains, by Planck's own later measurements, the single largest component of everything that exists, over 2/3 of the entire universe by mass and energy, and one science still can't explain. The Nobel Committee's own summary of the discovery put the stakes about as plainly as physics ever does. After studying dozens of these exploding stars, the laureates found that the universe isn't just expanding, it's expanding faster and faster. A result the researchers themselves reportedly found startling when their own data first came back. We've spent this entire video talking about scale, distance, and structure, but there's one more scale worth touching on before we close. The natural question all of this raises about how many other worlds might actually be out there, in a galaxy this large, holding this many stars. NASA's Kepler Space Telescope, launched in 2009, spent its primary 4-year mission staring at a single, fixed patch of sky, watching for the tiny, repeating dips in starlight caused by planets passing in front of their host stars. By the time that mission wound down, Kepler had identified 4,034 planet candidates, more than 2,300 of which were later confirmed as real, and it had done all of that while observing only a tiny sliver, roughly 1/400th, of the Milky Way's total stellar population. Extrapolating outward from that sample, early analysis by the Kepler team suggested there could be at least 50 billion planets in our galaxy altogether, with roughly 500 million of them sitting in the habitable zone of their star, the not too hot, not too cold band of distance, sometimes nicknamed the Goldilocks zone, where liquid water could plausibly exist on a rocky surface. A more recent, more conservative analysis of the complete 4-year Kepler dataset, led by researcher Steve Bryson and published in 2020 using all 4 years of original mission data, narrowed the estimate considerably, restricting the count specifically to Sun-like stars and truly Earth-sized rocky planets sitting in that same Goldilocks zone. That tighter, more careful analysis landed on a figure of at least 300 million potentially habitable planets across the Milky Way, with researchers noting that a handful of the closest candidates could plausibly sit within just 30 light-years of our own Sun. As SETI Institute researcher Jeff Coughlin put it at the time, this was, in his words, the first time that all of the pieces have been put together to provide a reliable measurement of the number of potentially habitable planets in the galaxy. It's worth being precise about what that number does and doesn't mean. It's an estimate of how many planets could plausibly support liquid water based on their size and orbital distance, not a claim about how many of them actually host life, which remains completely unknown. That many potentially habitable worlds raises an old, uncomfortable question, one that's been sitting underneath this entire video without being named directly, so let's name it before we close. In the summer of 1950, physicist Enrico Fermi was walking to lunch with a group of colleagues at the Los Alamos National Laboratory in New Mexico, reportedly in the middle of a casual conversation about flying saucers, when he stopped and asked a simple question: "Where is everybody?" Fermi wasn't the first person to raise the underlying idea, but his name is the one that stuck to it, and the question became known as the Fermi paradox. The paradox, stated plainly, is this: given the sheer number of stars in our galaxy, the huge number of those stars likely to have planets, the hundreds of millions of those planets sitting in potentially habitable zones, and the roughly 13.8 billion year age of the universe, more than enough time for even a slow, sub-light speed spacefaring civilization to spread across the entire Milky Way, somewhere on the order of 100,000 years of travel time at most. We should reasonably expect to see some evidence of other intelligent life by now. And yet, despite decades of dedicated searching, we haven't found any. In 1961, astronomer Frank Drake, who a year earlier had led the first serious organized search for extraterrestrial radio signals, a project conducted from the National Radio Astronomy Observatory in Green Bank, West Virginia, and aimed at 2 nearby Sun-like stars, proposed a framework for thinking through the problem more rigorously, now known as the Drake equation. He introduced it during a follow-up meeting at that same Green Bank facility, attended by a small group of scientists that included a young Carl Sagan. It doesn't produce a single confident answer. It's a chain of multiplied factors: the rate of star formation in the galaxy, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction where life actually develops, the fraction where that life becomes intelligent, the fraction that develops the technology to communicate across space, and finally, the length of time such a civilization would keep broadcasting before falling silent, whether through collapse, disaster, or simply moving on to other forms of communication. Many of those factors remain genuinely unknown, which means the equation's final answer can swing wildly, from confidently predicting a galaxy teeming with other civilizations to suggesting we might, statistically, be alone in it. Plug in a short enough average lifespan for a communicating civilization, on the order of 1,000 years, and the math can spit out an expected number of detectable civilizations in the entire galaxy of well under 1, meaning that, statistically, we might be it. We're not going to pretend to answer that question in this video, because nobody actually can, not yet. But it's worth sitting with the shape of it on the way out. Everything we've covered, the 100,000 light-year galaxy, the hundreds of billions of stars, the hundreds of millions of potentially habitable worlds, the trillions of other galaxies beyond our own, all of it adds up to a universe that looks, by the numbers alone, like it should be full. And as far as we can currently tell, looking out from this one small, spinning planet, it's silent. Either way, take the more conservative of those two exoplanet figures, 300 million, and sit with it for a second next to everything else in this video. 300 million planets, each one potentially capable of holding liquid water on its surface, scattered across a single galaxy that is itself just one of somewhere between a few 100 billion and 2 trillion galaxies in the observable universe alone. We've spent this entire video trying to make the Milky Way feel small next to everything larger than it. It's worth remembering, on the way out, that the Milky Way itself, small as it now looks, might still be home to hundreds of millions of worlds we've never even glimpsed. And, as far as we currently know, not one confirmed voice besides our own. Let's slow down for a moment and just sit with the picture we've built, piece by piece, because it's worth letting it settle rather than rushing straight past it. Picture Earth first, a small rocky planet spinning quietly, orbiting a fairly ordinary star we call the Sun. Around that star, in roughly the same flat plane, the other planets trace their own slow circles, and beyond the last of them, Neptune, at about 30 times the Earth-Sun distance, the material doesn't just stop. It thins out into the Oort cloud, a faint, sparse shell of icy bodies drifting in the dark, stretching out to somewhere around 2 light-years from the Sun. That whole structure, star, planets, moons, comets, and the Oort cloud together, is our solar system. It is, on the scale we're about to describe, almost nothing. Now picture that entire solar system as a single point of light, and picture 100 billion more points just like it, some brighter, some far dimmer, some paired together, some alone, scattered across a flattened, spiraling disk of stars 100,000 light-years wide and 1,000 light-years thick, held together, we now know, mostly by a form of matter nobody has ever directly seen. That disk has arms curling out from its center like a pinwheel caught mid-spin, arms that astronomers are still actively arguing over the exact number and shape of, and our own solar system sits inside a minor arm called the Orion Spur, tucked between two much larger structures, the Sagittarius arm and the Perseus arm, roughly 2/3 of the way out from the glowing, crowded bulge at the center. At that center, unseen, sits an object with the mass of 4 million suns, folded into a space smaller than the orbit of Mercury, quietly holding the entire structure together with gravity alone. Every star in that disk, including ours, is slowly circling that invisible point, and our own circuit takes somewhere around 250 million years to complete, just once. And underneath all of it, wrapped around the entire visible disk in a vast, invisible halo, sits the roughly 90% of the galaxy's mass that isn't made of stars at all, dark matter, detected only by the way it bends the paths of everything we can actually see, first hinted at by Fritz Zwicky in 1933, and finally proven, decades later, by Vera Rubin watching the stars of Andromeda refuse to slow down the way gravity said they should. That entire spinning structure, 100,000 light-years across, mostly invisible by mass, and quietly still digesting the wreckage of at least one ancient collision with another galaxy entirely, is the Milky Way. It is our galaxy. It is, as far as we know, the only home our species has ever had, and it may hold, by conservative modern estimates, somewhere upward of 300 million planets sitting in the narrow habitable band around their stars, worlds we've barely begun to count. And it is, itself, one single point of light in a much larger darkness. Roughly 2.5 million light-years away sits Andromeda, larger than our own galaxy, holding perhaps 1 trillion stars of its own, drifting slowly closer to us, across a gulf of space so vast that the light we see from it tonight left before modern humans existed. The same faint smudge a Persian astronomer wrote about in the year 964, long before anyone knew what it actually was. Around both galaxies, and roughly 50 smaller ones besides, including the large and small Magellanic Clouds, visible only from the southern hemisphere and slowly spiraling in toward their own eventual absorption, gravity has drawn together a loose association we call the local group. And the local group itself is only a small piece of something larger still, a slow, vast supercluster called Laniakea, 500 million light-years across, 100,000 galaxies strong, all gently sliding along invisible channels of gravity toward a shared low point in space that astronomers call the Great Attractor. We are near its edge, not its center, just one unremarkable galaxy among 100,000 others, inside a structure that is itself slowly coming apart, destined to disperse as the universe keeps expanding around it. And beyond Laniakea, beyond every supercluster we've ever mapped, lies the observable universe itself, a sphere 93 billion light-years across, still glowing faintly in every direction, with the leftover microwave afterglow of its own birth, first stumbled upon by 2 radio astronomers trying to figure out why their antenna wouldn't stop hissing. That sphere holds some number of galaxies, a few 100 billion by one recent estimate, as many as 2 trillion by another, that no one has yet managed to pin down for certain, including some, glimpsed only in the last couple of years by the James Webb Space Telescope, that existed when the universe itself was less than 300 million years old. Beyond the edge of what we can observe, there may be more. There may be far more. There may, for all current physics can tell us, be no edge at all. This is the actual, literal place you live. Not a metaphor, not a rounded-off estimate meant to sound dramatic for a video, but the real, measured structure of the universe, built layer by layer out of a century of careful astronomical work, from Henrietta Leavitt's Cepheid stars in 1912 to Edwin Hubble's flickering star on a photographic plate in 1923 and his discovery of cosmic expansion 6 years later, to Vera Rubin's flat rotation curves in the 1970s, to the Event Horizon Telescope's first image of our galaxy's black hole in 2022, to research being published and revised as recently as this year. It's a strange thing to hold both halves of that truth at once. On one hand, everything you have ever known, every person you have ever met, every place you have ever been, exists on a single small planet, orbiting a single ordinary star, tucked into a minor arm of one galaxy among what might be trillions, itself made almost entirely of a substance we still can't directly see. On the other hand, that same tiny vantage point is the only place from which any of this has ever actually been measured, mapped, and understood. Every number in this video, the width of the galaxy, the mass of its black hole, the age of its oldest stars, the distance to its nearest neighbors, the composition of the universe surrounding all of it, was worked out by people standing on that same small, spinning rock, looking outward, and slowly, patiently, figuring out just how big the room actually is that they've found themselves living inside. A Persian astronomer squinting at a smudge of light in the year 964. A woman cataloguing faint stars for 30 cents an hour in 1912. A young astronomer marking a photographic plate in red ink in 1923. 2 engineers cleaning pigeon droppings out of an antenna in 1964. A team combining 8 radio telescopes spread across an entire planet in 2022. None of them had more to work with than what could be seen, measured, and calculated from right here, and together, over the course of about a century, they built the picture we've spent this entire video walking through. You already knew, before you clicked on this video, that space was big. Now you know some of the actual numbers behind that feeling, the ones that hold up under measurement, under peer review. under a century of astronomers checking, rechecking, and occasionally overturning each other's work. From a galaxy's diameter, to the mass hiding inside its dark matter halo, to the 50-50 odds of its own eventual collision with its nearest neighbor. And the next time you're outside on a clear night, and you look up at that faint, pale band of light stretched across the sky, the one Democritus first guessed, correctly, was made of countless individual stars, you'll know you're not just looking at a pretty smear of light. You're looking at the edge-on view of the very structure we've spent this entire video trying to measure. A structure still being cannibalized, still being weighed, still being redrawn one telescope generation at a time. You're looking at home, and you now have a much better sense of just how small, and how strange, and how genuinely unfinished our understanding of that home actually is. A home that is, by every number this video has walked through, somehow both the only place we have ever known and a single, unremarkable speck inside something almost too large to hold in mind at once.